When we talk about AI workloads, it's easy to focus on just raw compute power. But the truth is, they present these unique infrastructure challenges that go far, far beyond that. Real success requires a dedicated, structured approach to engineering the entire system that supports them. So the core idea here is that AI workloads really demand a formal, disciplined engineering process. In this explainer, we're going to walk through Sismatik's 5-step framework for how to properly design, deploy, and then optimize these really complex enterprise-grade AI environments. All right, let's start with the most critical phase. Step 1, workload assessment. This first step is all about a deep, multifaceted analysis to really define the unique DNA of the AI workload. We're assessing the model's architecture, the parameter scale, the size of the dataset, all of which directly tells us about the compute and memory requirements. We also analyze the training cycles, inference demands, and, this is absolutely critical, the communication patterns between the nodes. That's what's going to dictate the entire network topology. You see, each of these factors comes together to create a really distinct performance profile. This detailed analysis gives us the clarity we need to define the infrastructure baseline. Seriously, all the engineering decisions that follow are built right on top of this foundation, because any guesswork at this stage just leads to major performance headaches later on. So with that foundational understanding locked in, we can move on to step 2, infrastructure architecture design. Now, this is where we translate that workload analysis into a real physical and logical blueprint. This means designing the GPU cluster topology, specifying the high-speed network fabric, things like InfiniBand or RDMA over converged Ethernet, and aligning the storage performance perfectly. We model for redundancy and engineer for key metrics like interconnect bandwidth and latency sensitivity. The main goal here? To design a balanced system that completely eliminates any potential I/O bottlenecks. And this is so important because it ensures that those very expensive GPU resources are actually spending their time computing, not just sitting stalled waiting on data from storage or the network. Optimal performance isn't an accident. It's the direct result of very deliberate engineering. Now, AI workloads are almost never static, right? They grow and they evolve. And that brings us to step 3, capacity and scalability modeling. The infrastructure just has to be designed for modular growth. So we model these expansion scenarios right from the very beginning. We plan how a system can scale from a starting point of, say, 8 GPUs all the way up to 128 or more, and do it without needing a massive, disruptive architectural overhaul. This means we have to plan for that long-term growth from day one. We analyze factors like network switching capacity, rack density, power distribution, and even cooling thresholds to make sure the data center itself can actually support that future expansion. The guiding principle here is that scalability simply cannot be an afterthought. It has to be a foundational component of the initial design. If it's not, you're just setting yourself up for costly and really disruptive re-engineering down the line. Okay, with the design finalized, we get to move to step 4, deployment and integration. This is the methodical process of actually bringing the design to life. It starts with provisioning the physical infrastructure, and then it's followed by detailed hardware configuration. But we don't stop there. Then we move into performance validation, which means rigorous benchmarking and stress testing. And finally, we integrate the new environment with any existing systems, making sure everything's compatible across all the layers: compute, storage, and orchestration. And the result of this whole methodical process is a stable, thoroughly validated, and production-ready infrastructure environment, one that's been engineered specifically for that target AI workload. But the work isn't done once it's deployed. Infrastructure performance has to be actively managed. This brings us to the final phase, step 5, optimization and lifecycle support. This is all about sustaining that performance over time. It involves continuously monitoring the entire stack, doing detailed analysis of GPU utilization to make sure they're not being underused, and constantly assessing storage throughput. It also includes forward-looking expansion planning to make sure the system continues to meet evolving demands and maintains its operational resilience for the long haul. At the end of the day, you can't treat AI infrastructure as a set-it-and-forget-it kind of deployment. It's really an evolving engineering system, and it requires continuous attention and refinement to maintain that peak performance. So, to sum it all up, this 5-step methodology treats AI infrastructure not just as a collection of components, but as a cohesive systems engineering discipline. The result is a process that is intentionally structured, it's inherently scalable by design, and it is relentlessly focused on delivering measurable performance. This disciplined process is exactly what it means to engineer the high-performance infrastructure behind intelligent systems. It's the very foundation upon which the future of enterprise AI is being built.